So, our next speaker here is Laurence Barker, G8NJJ, and he's going to talk about the completion of the Saturn SDR. Please give him a warm applause, warm welcome.
Okay, good morning everyone. I've come and presented bits about Saturn before, so I kind of got the idea started here about 5 years ago. I gave a tutorial on the FPGA side a while ago, and I talked last year about how we've connected the software on the Raspberry Pi into the hardware. Today I'm just going to give some thoughts about finishing off the whole project, because most of it was done more than a year ago. So this is my prototype of the Saturn radio. Why do I do this? Well, it was the radio I wanted to have. I wanted to be able to say that this is my HF transceiver. I wrote the code that's in that, and I've written all the FPGA code. I've written most of the Raspberry Pi code, bits of some of the SDR applications that run on it, and it just gives me pride to be able to say that's the thing that I made happen. So it's in an Apache Lab chassis. It's got an RF board with a 100-watt power amplifier underneath the silver you see there. It's got a Raspberry Pi processor, and it can run the Pihpsdr application. And at last, it's finished. This is the picture I presented last year of Saturn itself. Saturn is essentially the DSP board behind that. On the left, it's kind of like a lot of Pihpsdr or other radios, really. There's an FPGA, there's two A to D converters, there's a D to A converter, there's a driver amplifier after the D to A converter, there's an audio codec and all the power supplies. On the right-hand side, that's pretty much like the schematic of a Raspberry Pi 4 compute module board. It's got the Raspberry Pi 4 itself there, and all of the interfaces you expect. The FPGA and the Raspberry Pi 4 joined together using PCI Express, and that's all working absolutely fine. So last year I came and I showed the first prototype board, and we had essentially most of a complete radio working at that point. Then one of the power supply chips on the board failed, and we had about 3 months where we could do nothing at all. We got a second version of the PCB about Christmas time, and we got everything back up and running, and the board was absolutely reliable from that point onwards. So I don't know if you know the Pihpsdr protocols. This is the bit that would sit between an FPGA-based radio and a PC, using typically Ethernet nowadays. The first code that I wrote was a server for what was called Protocol 1, that was quite a simple fixed sample rate application. I've now written a Protocol 2 client, Protocol 2 server. That enables all of the functionality in my SDR board to be used. So up to 10 DDCs, for example. And quite quickly, I had everything working that we expected to be working. It's quite unusual for my code to work first time, and that bit of code really just did. So we had two receivers, we had antenna diversity, and we had the pure signal pre-distortion code, all working quite happily on the radio. One thing that I'd spotted quite early on, right in the middle of the passband, is a DC spike. That is, when we first started out, about minus 70 dBc, far too high, and something had to be done about that. I left it until we got everything basically working before going back to find that error. But it was an error I had to find and I had to fix. Well, many years ago, when facing this kind of problem, I learnt that the right way to approach this is you simulate something rather than try and make hardware changes and just dabble about. What we were looking for was a rounding error somewhere in the maths. It's quite simple. The maths of the down conversion and filtering is quite simple, and somewhere in there was a rounding error. Well, to test that, you need bit-accurate simulation. And Vivado's, that's the Xilinx FPGA design tool, gives you a simulator that is bit-accurate. And that can quite easily give me a simulation in the time domain of the I and the Q channel of the signals, which is what is in the red blob. Problem with that is you can't see the DC offset because we're looking for something that's about 1,000th of a pixel. To make any progress, we'd need to be able to look in the frequency domain, and Vivado can't do that. So I thought I had three options. One was to just make changes to the hardware and see if it made a difference. It was quite fast to find out, quite slow to recompile each time, and there was no diagnostics. I couldn't find out anything in between the A to D converter and the output onto a PC application. So that would be like stabbing around in the dark. There was no way of knowing whether what I was doing was the right thing. So there's no science. I could create a software model of the process, and that could be written in C or MATLAB. That would be reasonably quick to run, and that would probably work as well. It's quite easy to write with MATLAB, but to do that, you need a whole load of libraries, and for me, that would have cost several tens of thousands of pounds that I don't have, so I couldn't use that route. Or I could use the Vivado simulator and get the data out from the simulator and find another way to plot that data. So that's the route that I tried taking. Vivado gives me a bit-true cycle-accurate simulation, which is exactly what I need for looking for rounding errors. What I needed to do was to get the IQ samples out from that into some way of plotting them. I spent some time trying to find out how to export data from Vivado, and that turns out not to be the right thing to do. The right thing to do is to write a test bench. So a Verilog test bench on the right-hand side here essentially wraps around the simulation of the FPGA, and I was able to get it to dump out some intermediate data and write that to a file. Don't try and read that or write that down. It's all in my repository if you want to look at it later. So writing a file out of 1,024 samples or 4,096 samples is very easy to do. All I then had to do was to plot that. And I came across a tool called Octave. Many of you, I imagine, will know Octave. It's kind of like a copy of MATLAB. Very similar language structure, very similar libraries, although there's a lot fewer of them publicly available, but that is there is all free to use. What I needed to be able to do was to read in an array of IQ samples, do a fast Fourier transform to convert that to the frequency domain, and then generate a plot so that I could then see what the spectral content of that was. And with some help from my son Michael, I was able to get that up and running round about Christmas time, and we were able to get the IQ samples in and do a simple FFT. And from that, we were able to find that, yes, we could see the DC spike, and we could then start making some progress in trying to fix it. Oops, it's not, there we go. Well, the first thing I found out, I put some debug outputs onto the complex multiplier output at this point, and I couldn't see the DC spike there. I put some debug onto the cascaded integrator comb filters, and I could see a DC spike. So that told me that the problem wasn't in the FIR filter, it was before that. CIC filters are essentially like a cascaded add and then cascaded subtract system, and they're quite well known for having overflow issues and needing quite long word widths to avoid overflow issues. So that seemed an obvious place to start. first thing I did was to try changing the input word width by giving essentially a much larger input word to the CIC filter by changing the output width of the complex multiplier. That didn't seem to make a difference. To make changes to the width within the CIC filter, it wasn't something I had any control over. I was using a Xilinx IP block. And already, when you look at the data, it's already using quite big word width, so more than 60 bits in the adders and subtractors in that core. The things that I could change were the input width, that didn't seem to make a difference, and the output width, which did seem to make a little difference. So I was able to make some kind of an improvement. And I could get to the point with a 32-bit output from there that I couldn't see my DC spike anymore. So I thought maybe that I fixed it. Go back to Vivado, make that change into the main FPGA code, compile that and run it on the Saturn radio hardware, and sure enough, I had made a substantial improvement, but there was still a spike 20 dB above the noise floor, so it wasn't fixed. And the problem at that point, you realize that when you look at the spectrum display on an SDR program, you might be looking at 100 kilohertz of spectrum. So one pixel might be 100 hertz. When I look on the Vivado code, where I was dumping out the entire band with, say, a 1K or a 4K FFT, each pixel was maybe 120 kilohertz. So the noise floor was 30 dB higher. So as you go into the radio and zoom into the signal, you're pushing the noise floor down, you can see smaller spurious signals. And that's why I wasn't seeing it. So I would need to use a much longer FFT to be able to get the data out from Vivado and look at it in Octave. Well, to collect 1K of data to do a 1K FFT, Vivado was taking about an hour to run its bit-true, cycle-accurate simulation. To get a 4K FFT, that was possible. It took about 4 hours, but you can do that. If I wanted a 64K FFT, that was going to take 3 days, and that really wasn't very practical. Then I thought maybe I need to do some thinking. And once I thought about it, the problem was all down to those FFT filter widths. Because of the noise floor, I hadn't seen a spike on the complex multiplier output, but that's where the spike was, and it was just hidden by the FFT noise floor. And the rounding error was in the complex multiplier itself. And the way to fix that was quite easy. The Xilinx IP core has a way to support random rounding, so by giving it a random number input, it will either round up or round down on each individual cycle according to the setting of that random number. And that's quite easy to introduce. So in my complex multiplier over here, I've got an input from the A to D converter, I've got an input from the DDS that's generating the local oscillator, and I've now got a 1-bit random input in the orange color from a random number generator. Generating a random number that changes each clock cycle is very, very easy to do. You use linear feedback shift registers, and the Verilog code for that is on the right-hand side, and that's kind of all that you need to do. And put that into the simulation, rerun that, and it instantly fixed the problem. There was no DC spike at all. So that was the problem all along in the complex multiplier, and easy to solve. So a lesson from that, don't jump to conclusions. I was seeing something and believed that what I was seeing was right, and not looking far enough as a consequence. A 1K FFT with a sample rate of 120 megahertz is not the same thing as a 1K FFT with a sample rate of 48 kilohertz. And it turns out if I dug a bit further, I could have got a C bit-true model of that CIC filter. It's something that Xilinx do make available. So maybe I could have written a complete software simulation anyway. I didn't find that till it was too late. Just for entertainment, I've then gone on from there and written a complete Octave model of the whole digital down conversion process. That meant adding in a CIC model and an FIR filter model. I haven't actually found anything I need to do with that yet, because I've kind of solved the problem, but it's there next time. One thing we found was that pure signal stopped working. Pure signal is a pre-distortion algorithm for transmitter improvement developed by Warren NR0V, who's presented about this program in this audience before. Something that I changed when I was finding that DC spike stopped pure signal from working, and it wasn't at all obvious what. It turns out that in going through that process, the maximum output amplitude of essentially data coming out from my IQ down converter more than doubled in amplitude, and it was then using the full dynamic range of the 24-bit data. And pure signal is sensitive to that maximum amplitude, and it needed essentially to be told what the maximum signal level, and a one-line change to the DSP application instantly fixes that. So that's a problem that was able to go away quite quickly. So what else have we done? Well, we've added some more features into the protocol too. It's not a client, it's a server application. That's what runs on the Raspberry Pi code and makes the IQ data available to PC applications. We've added a few things into there that can report the software version. We can select a balanced microphone input as well as the single-ended microphone input that's already on the board. We've got a fallback configuration for the FPGA now, so if you're downloading new FPGA code and the power files, everything isn't lost. There will still be a configuration that the FPGA will boot, and you can run the process again. We've added the CW Kia code into the FPGA. That's the same code that's in other Pihpsdr radios. And we've created some test applications. One is for testing microphone level so that you can see if your microphone's working and the PTT input and whatever are all working without connecting to a transmitter. And we've got a little app to be able to set up the bias levels of the PA and the PA driver. I've had some help from Rick, N1GP, in helping to find and fix some of the issues we've had in the radio. And thank you to Rick for that. The Pihpsdr application is the one that I want to run on the radio. This was originally written by John Melton, G00RX, and John has presented about this program here before. There's been some changes made to it by Christoph, DL1YCF, and Rick, N1GP, and that's resulted in a capable program that's got modern signal processing code built into it, the same signal processing code that is in the Pihpsdr Thetis application. But the whole lot runs on the Raspberry Pi. It gives you a display that is kind of what you expect to see on an SDR, and it works within the confines of the Raspberry Pi processor. We had that working quite a while ago. Rick has modified that so it will pull data straight from the FPGA rather than going via the Protocol 2 application. So it cuts out the middleman, if you like, so it's now got no barriers in the way of its data path. And that gives us a complete standalone radio. Rick's then gone further. What we had 2 months ago was essentially the Saturn hardware with connection via the various hardware registers in the FPGA to Pihpsdr, and that worked fine. What Rick's then done is add the Ethernet server into Pihpsdr so that another client application, Thetis or something else, can then take data from the radio but via Pihpsdr. And what that means is both clients can run at the same time. So we can have one user using Pihpsdr locally on the radio, another one connected via Ethernet, using more of the radio's resources. There are 10 digital down converters available, potentially looking at other bands or whatever. Either of those radios can transmit, and there's a way of choosing which one transmits. Some interesting multi-operator things might be possible from that in multi-operator contests, for example. So where do we go? Well, version 1 of Saturn is essentially finished, but there is always going to be more that we can do. And that's one of the things that's interesting about it, really. If I want to add some more signal processing into the FPGA, I can do that. If I want to add some more processing into the Raspberry Pi side, I can do that. The thing that I want to go on to do next is put some more features into the Pihpsdr program, so that to improve its display. Does anybody else want that? I don't know, but it's something that I would like to see, and because it's all open software, it's something that I can work on. But there's a lot more we can do beyond that. It would be quite interesting to see if we can connect a thin client to the radio in some way, so that a remote user connected through the internet can use its receiver or its transmitter. I note there is a presentation on a thin client application this afternoon, so that might be something that is worth talking about at that point. There might be more that we can do with the FPGA. We've used a relatively large FPGA. There's a lot of resource not used in that. Does it make sense to move some processing into the FPGA to lighten the load on the Raspberry Pi? It's possible. Doing the display processing, doing the display FFT in the FPGA might be possible, for example. There are several steps in the WDSP path before the FPGA, but they look like before the FFT for the display, but they look like relatively simple applications that would be amenable to coding in Verilog, so that might be something we could do to increase the throughput. So essentially, that is my radio completed to a first version, but I will still be working on it. Does anyone have any questions?
Yes, thank you very much, Laurence, for your great contribution. I think we were talking about the FPGA and the improvement of the audience to use it, and this was a good contribution for that. So, what are your questions? Any questions on that? Comments? Nobody doing FPGAs? Yeah.
What I would say is 5 years ago, I didn't do FPGAs either. I learned, and it is possible to learn, and it's not as big a step as maybe you imagine. I was able to use the Xilinx IP building blocks, and your design process, you start with something that looks like a schematic, and you join blocks together. And it's only later I had to start writing Verilog, and it was a long, long time before I'm not even sure that I would say I'm competent at writing Verilog, but I can write some of it. It was a long, long time before I could do that properly, but I still got there just through trying.
And I can add that we will have one talk in the afternoon, which shows a very simple way using Python libraries to generate FPGA code. So it will be an we have a question.
Yeah, is it possible to synthesize the FPGA code using open source tools, or is that out of the question for Kintex 7, I think?
Open source, I don't know, but free to use, definitely. The Xilinx have tools that will synthesize from C, readily available, and there are whole books you can get. There's a book called the Zinc book that goes into quite a bit of detail on those. I've not personally tried them, but yes, those tools are available.
Okay. Yeah, Laurence eats the hard stuff. But thank you very much for the contribution. Very nice. I think we switch over to the next speaker. Markus, can you please introduce the next speaker? Thank you very much.
Thank you very much.